In this video, we're going to talk about something called sampling distributions. And sampling distributions are distributions that we make by measuring things about a sample from a population. Now, before we get going, we need to talk about a little bit of jargon. So we have these terms so we can refer to concepts. The first one is a population. Basically, you can think of a population as everything that you want to study. It's the totality of observations which we're concerned. A sample is some subset of that. So any usually smaller amount that you pick from the population. And we care about a particular type of sample. We want our samples to be random. So what do I mean by a random sample? Well, I mean that each member of the sample is chosen so that it's uniformly random, which means that each object that you're taking in your sample has the same probability of being picked, and independently. So choosing one object from the sample doesn't affect the probability of choosing a different object in our sample. So we like random samples. The other piece of notation we need is called a statistic. And a statistic is any number that you calculate from the sample. And the statistics that we're interested in are statistical concepts that we care about, like the sample mean and the sample standard deviation and the sample variance. And the whole idea why we're doing this, the whole idea is we usually have a population, and because populations are usually quite large, we don't know things about them. Like we don't know the population mean. So this is something that is fixed, but usually unknown. This exists, but it's really hard to figure out. So what we do is we try and estimate it. We try and take a guess by taking a sample and then calculating its mean, for example, and using that as a stand-in or as an estimate for the actual population mean. And that's kind of what we want to do here. We want statistics, we want them to estimate some population parameters. And by population parameters, I mean things that are true about the population themselves, like the population mean, the population standard deviation, and the population variance. Note the difference in notation here. So for samples, we kind of use letters, lowercase letters like x bar, s, and s squared. And for parameters, we use Greek lowercase letters. We use like lowercase mu and lowercase sigma. So just to be aware of the notation there, that's kind of the idea of what's going on. And a quick note, these aren't the only statistics, of course, that you can calculate from a sample. Maybe you could be interested in things like the range or the median. We could calculate statistics from those. We know how to do those, but for this course, we're going to primarily be interested in these here, and really we're going to focus on estimating the mean of a population. A quick example of this. So imagine we wish to determine a mean height and the height variance of students at Cape Breton University, and we wish to do this from a random sample. So what is our population? Well, we want to know the mean height of all students at CBU. So our population is all students at CBU. And there's about, as of right now, it's about 4,500 students. Now, how can we randomly sample these? Remembering that an important thing with random sampling is your choices need to be independent and have an equal likelihood of being picked. Can you determine a way of randomly sampling some CBU students? And pause the video and think about that. Okay, now that we're back, maybe if you took all of the names of students and you draw out a sample, a subset of names, so drawing names is one way of doing it. Or maybe you want to take, say, every 25th student in some list of all students. So that would be another option. Nothing special about 25th either. I just picked that number. That just gives us some sample of students. Or some other method. But be careful, one way that's not a random sample is, say, standing in the cafeteria on Friday mornings and asking people their heights. And the reason that that isn't a random sample is because different groups of students are more likely to get picked than others. Because, for example, a lot of business students do not have classes on Friday, so you would be undersampling business students. And a lot of athletes are on campus in the morning early, so you might oversample athletes. So you wouldn't get a random sample if you did something like that. And random sampling is very hard. You have to be careful about it. But that's for a later class if you go and do more statistics. The statistics that we're interested in, well, we're interested in the sample mean because we want to estimate the population mean, and we're interested in the sample variance because we want to estimate the population variance. Now I want to talk a little about sampling distributions themselves. First of all, what is a sampling distribution? And basically what it is, it's a distribution where the observations in that distribution are statistics from a sample. And in this case, we're going to worry about the mean. So it's going to be the mean of a sample. So let me explain kind of what's going on. So let's say we had a population, and the distribution of this population was highly skewed. So most observations in this population would be somewhere around here, so you're more likely to draw an element randomly from this population over here than you are over here. So hopefully that idea is helpful. And what we're going to do is we're going to build up a new distribution called the sampling distribution by taking an average of so many points and plotting them down here. So let's make a sampling distribution where we're taking samples of 5 observations. So let me kind of show you what's going on. We're going to draw randomly, we're going to draw 5 objects from this population. Remember, the population has this skewed distribution. So we're more likely to get things to the left than to the right. And if we do that, we should see that we took these 5 points here. So this has a value of 1, this has a value of 2, this has a value of 4, this has a value of 5, and this has a value of something along the lines of 10. And then I take the average of those, I add them together, I divide by 5, and I get what it looks like 1, 2, 3, 4. 1, 2, 3, 4. So I get a value of 4 here. The average of these 5 points is 4. And I keep going. Let me do it once again here. So I took another sample of 5 points. In fact, I did it twice here. I did it while the video was paused. I got another sample of 8, and here's a sample of 9. I took these values here, and I took the average of them, and I got, in this case, 9. And I can continue like that. And you can see we did another one, took the average of those 5 points, and we got 11. So hopefully you can see the idea of building up this sampling distribution. Let's do a bunch more in a row here. So there's 5 more, and another 5, and another 5, and let's just do 10,000 of these. So you can start to see the shape. Even though we started with this nice skewed distribution here, our sampling distribution, where the points are now averages of 5 observations from our population, it starts to look fairly normal. Not completely normal. I'll put a normal curve here. So you can see it's still a little bit skewed to the right. You can see that we have this longer tail, just slightly longer over here. So it's slightly skewed to the right. But one thing that you can notice is that the means here are roughly the same. So the mean of my population distribution is just over 8, and the mean of my sampling distribution is again just over 8. The medians are different, and we'll talk about that in a second, but we'll focus on means here. We see that the means are roughly the same. So let me do another 100,000 of these, just to get an idea of what's going on. So there's another 100,000, and now you can see the means are very, very close to each other. And if we did more and more points, we would find that the means are exactly the same. So let's do this again. Let's change some things. Maybe let's change the number of sample points we're taking. Let's have fewer sample points. Let's have 2 sample points. So again, I'll do an animation just to see what's going on. We draw 2 from our sample, we take the average, and we plot that point. So we're going to do that a bunch of times. Let's do it 5 more times, and we get something like that. Let's do it 5 more, and let's do 10,000 more, and we get something that looks like that. So I have that normal curve still fitted there, and you can see that we have fewer points, so it doesn't look as normal. It still is taking on more of the shape of the original population distribution. What happens if we change this so that we have more sample points? So let's change it from 2, let's go to 25. Again, I'll just animate one of these and then do a whole bunch of others. So if we do a sample of 25, here is our 25 being drawn here. You can see that there's more points being drawn from the lower end of the distribution than the higher end, and we take the average of those and we put that point there. So let's do that 10,000 times, 100,000 times, and you can see that here we have something that looks very, very normal. It doesn't look particularly skewed at all. So it seems that the more points we have in our sample, the closer the sampling distribution looks to normal. So here's a very skewed distribution, but this kind of thing will hold for any distribution that you like. So what I did is I posted a link for this, or here's the website here if you don't have access to that link. Go to this app and play around with it. You can choose various distributions by changing here. In fact, there's one option where you can draw your own. It's called the custom distribution. And you can change the number of points in your sample here. And you can always fit the normal curve just to see how close it is to a normal distribution here. And what I'd like you to do is go to this app and play around with it. Determine how the sample size affects the shape of the sampling distribution. Determine how the shape of the population distribution affects the shape of the sampling distribution, especially when you have a small sample. And pay attention to the mean and the standard deviation of the population distributions and the sampling distributions, and see if you can notice some patterns that are happening. And then we'll talk about that on the next slide. So pause the video now, go to that website, and play around and see if you can notice some things. So, hopefully you've found these 4 observations. There may be others, but I think these are the most important observations to make. So the first one is that as you increase that sample size, so n here is our sample size, the sampling distribution always looked more like a normal distribution. The second thing to notice is about the standard deviation. Well, as you increase the sample size, the standard deviation of the sampling distribution keeps getting smaller. In fact, it gets smaller in a way we can predict, which is really nice, but we'll talk about that a little bit later. The third thing you might have noticed is that the mean of the sampling distribution was always the same as the mean of the population distribution. Maybe it was off by 1 or 2 hundredths or something like that, but if you added more and more points, you would find indeed that the means are identical, which is very nice. And the fourth thing I want to notice, and it's kind of not a new thing, but if you played around with the various distributions and you were drawing your own, even if you drew something that looked pretty wacky, that barely looked like something that would occur, maybe you drew something that looked with a bunch of peaks, something like that, this would still hold. These 3 points here would still hold. So that's really interesting, and in fact, these points are always true. So, all of this together is basically what makes up the central limit theorem. And in some sense, this is the most important result that we're going to learn in this course. This allows us to basically convert any statistical question we have about a mean of a population to a statistical question about a normal distribution. And that's really, really powerful because we only need to know things about the normal distribution. So what does this say? It says, if we have kind of this random variable, let's call it big X bar, if this random variable is the mean of some random sample of size n, just like we did in that app, and we're taking it from a population, could be any population you like, that has a mean, let's say mu, and standard deviation sigma, then the distribution of these means, these sampling observations, that is the mean of our sample, that distribution approaches a normal distribution as n gets bigger. Moreover, the mean of that distribution is the same as the original population, and that's key. And the standard deviation isn't the same, but it changes in the same way. It's going to be the standard deviation of the population divided by square root n. And the important thing here is this holds for any distribution that you like. It can be as wacky and as asymmetric as you want. This will always hold, which is a very, very powerful result. A few notes here. So, first of all, if our population is normal distribution, we're kind of in luck. That's the best case scenario for us in some sense. So that says no matter what size our samples are, so it could be 1 or 2 or 3 or whatever, that sampling distribution will always be normal. So if we know our population distribution is normal, then we know our sampling distribution is normal, but that's if we know what the standard deviation is. Sometimes we don't, and then we have to kind of estimate it, and it will change things. But it's really nice if we have a normal population distribution, we know that the sampling distribution will also be normal. You can go back to that app and check that out as well, and you'll see that's the case, even for small n. In the other instance, if we have wacky distributions, it won't look normal until n is quite large. And what does quite large mean? Well, usually in statistical textbooks, they say that as long as your sample size is 30 or above, you can be safe saying that the sampling distribution will be close enough to normal to be able to use normal tables and whatnot. And the third point here is just a little bit of notation. So the mean of the sampling distribution, we just use mean of this, and we put a little subscript of x bar here to say it is the mean of this sampling distribution, where the points are the means of samples. And the standard deviation of that distribution, we just do the same thing, sigma with an x bar here. And from the center limit theorem, we know that, hey, the mean of the sampling distribution is the same as the mean of the population distribution. And the standard deviation of the sampling distribution is the same thing as the standard deviation of the population distribution over root n. And also, we usually call the standard deviation of a sampling distribution, we call that a standard error. You might hear that as well. So just be cognizant of that. We'll use that language later on in the course as well.